In today's class, we'll be seeing acoustics. So acoustic deals with sound, we know that, and we'll first talk about some parameters of it, and then we'll proceed with other formulas. So imagine this is your wave, okay, and the above part is called your crust, and below is trough, and in sound waves you also call it as compression and rarefaction. Okay, so the distance between two consecutive crust or two consecutive trough is called your wavelength. Okay, so this distance is your wavelength. Okay, and the distance between your normal and either your crust or your trough is called your amplitude. So these distances, they are your amplitude. Okay, so I'll write it down. Wavelength is represented as lambda. It is the distance between two consecutive trough or crust. Now imagine a scenario. Okay, in these two scenario, here your wavelength is short and here your wavelength is long. So in louder sound you have shorter wavelength. So this is your louder sound. Louder sound has shorter wavelength, while softer sounds have longer wavelength. And the unit of measurement is meters. So unit is meters. Okay, now we talked about wavelength. Let's go move on to amplitude. Amplitude is the distance between the trough and the normal, or crust and the normal. Okay, so amplitude distance between the normal and the crust or trough, and it's also measured in meters. So let's also again consider two scenarios. Okay, so these are your amplitudes. In softer sounds have shorter amplitude. Whereas you can see in louder sounds you have longer amplitude. Okay, then you have time period. So time period is the time required to produce one complete wave. Is your time period, which is the time taken to produce one complete wave. And of course its unit is seconds. Then you have frequency. Frequency, it can be denoted as f, and sometimes it's also called as no. This looks like gamma. It's also represented as no, but frequency is the number of sound waves produced in unit time. Is your frequency number of sound waves produced in unit time, and its unit is hertz. Then you have velocity. Velocity is the distance covered by the sound wave due in 1 unit of time. Okay, so velocity is the distance covered in unit time, right? And the distance covered is your wavelength, so which is lambda. So your v can be written as lambda by unit time taken, so t. And 1 by t is your frequency. It has a relation like that. So here you can write v is equal to wavelength into frequency. And this is known as wave equation. It is common to all sorts of wave, not just sound waves. So this is your wave equation. Then you have some properties of sound, right? So we have properties of sound. Whatever properties that we talk, like your wavelength, amplitude, frequency, everything is real parameters, like it's actually there. Whatever that I'm going to talk about now is your more psychological parameters, something that you feel, something depends upon how you hear it. Okay, so you have pitch, you have loudness, and you have timbre. And everything, all of these are your psychological. Okay, so pitch is basically how sharp or how um so pitch is basically how sharp or how low your sound feels or how you hear it. Okay, so how sharp or low the sound feels. And loudness is how loud or soft the sound feels. Like pitch has a lot to do with music and stuff. Loudness can be like your whisper is more softer sound, while talking is more louder sound. So that is how loudness is defined. And pitch depends upon the frequency of sound, while loudness depends upon the amplitude. And pitch does not have like a unit of measurement. They say it is perceived in mils. It's not unit of measurement, it's perceived. You can't like basically measure it. Loudness is measured either in phone or zone. Okay, so these are the basic characteristics, and timbre talks about the quality or the characteristics of the sound. For example, a guitar and a violin can have the same pitch and same loudness, but you know the quality of it or the characteristics of it is different. So that is your timbre. Okay, so the quality or the characteristics that allows you to distinguish between the sounds of same loudness and same pitch. Okay, so this is your properties of sound, and now we'll start with more formulas and other related terms. Let's start with sound intensity. Sound intensity represented as I or denoted as I. It is basically the power of the sound divided upon the area on which it's incidenting. So I is equal to power by area. Okay, and the unit of sound intensity is watts per square meter. Now there are two factors here. So one is the threshold of sound intensity. Wait. So sound intensity at threshold of hearing and sound intensity at threshold of pain. So you have threshold of hearing and threshold of pain. For threshold of hearing, it's 10 to the power minus 12 watts per meter square. And for threshold of pain, it is 1 watt per square meter. Okay. So this is our sound intensity. Then we'll talk about sound intensity level. So you have something called sound intensity level, also called as SIL. So sound intensity level is measured in decibels. And here too you have SIL at threshold of hearing and at threshold of pain. So your threshold of hearing is 0 decibels and your threshold of pain is 120 decibels. Okay, now we will talk about the formula for sound intensity level. So SIL is equal to 10 to the log of sound intensity divided by I naught. And always the value of I naught is your threshold of hearing, which is 10 to the power of minus 12 watt per square meter. Okay. Now say for example, I'm just gonna do an example sum here. It's not, we'll do sums full-fledged later, but let's just consider an example now. Say there is a sound intensity of 10 to the power minus 3 watt per square meter, and they're asking you to find the sound intensity level, or sometimes they'll say what is the in the sound level of it at something dash decibel. So they're basically asking you to find it in decibels. So what do? You put 10 to the power log of 10 to the power minus 3 by 10 to the power minus 12. and you calculate and you get an answer. But there's a trick to do this. You can put this in your scientific calculator in the exam and find your value, but the trick is you consider this 3. Okay, you take this 3 and you add it with plus 12. So minus 3 plus 12, it gives you 9. And with this number, you multiply it with 10 and it will give you 90, right? So this answer is 90 decibel. Okay, so you take the power, add 12 to it, whatever you are getting, multiply it by 10, that is your decibel. There is a reverse way of doing it as well. Say for example, they ask you to find, like, okay, let's consider the same situation. You have 90 decibel and they are asking what is the sound intensity of it. So what do? You divide this by 10 first. So 90 by 10 gives you 9, and you subtract this by 12, you'll get minus 3, and you just put it to the power of 10. So 10 to the power minus 3 watt per square meter is the intensity. So this is a trick, and you can put it to formula if you want, but this is how you do it. Now, so I talked about the sound intensity level of formula, and we'll see the sound intensity like sound level range for few factors. So let's be the category daytime, nighttime, okay. In residential area, in daytime the sound intensity level can be up to 55 decibel, and the nighttime 45 decibel. Then you have commercial zones. In daytime it can be 65, in nighttime it can be 55. You have industrial areas then. In daytime it can be 75, and in nighttime it can be 70. And lastly, you have silent zones like your buffer areas and stuff. So in silent zone you have 50 decibels in daytime, and in nighttime you have 40 decibels. The key to remember is like this increases by 10, and mostly this decreases by 10 or 5. So that's how you remember it easily. And the threshold of not threshold, but any sound level above 85 decibel, if you are exposed to it for a longer period, it could cause permanent damage. So any sound level above 85 is considered hazardous. Okay, so remember the 85 level. Then we have, okay, so I talked about sound intensity level. There's sound power level, also written as SWL. You have sound pressure level, also written as SPL. Okay, and these terms are mostly used interchangeably, but I'll just like write the formula for each. So all are calculated in decibels. So decibels, decibels, decibels. And I talked about the formula here before. Your SIL is 10 to the power log of I by I naught, and your I naught is 10 to the power minus 12. Here your SWL is 10 to the power log of W by W naught. W is the power of it, power level. So W naught is again 10 to the power minus 12. So these, you can say like these two are more interchangeable. Okay, so you have sound pressure level now. SPL is 20 log of P by P naught. P is the pressure level, and P naught is 20 into 10 to the power minus 6. So this alone varies a bit differently. Mostly they'll ask you just sound intensity level. They could ask you like what is the unit value for sound pressure level or sound power level, like that. But remember this one formula which is more important, which is if they are giving you say sound power level and they are asking you to find the sound pressure level at distance, then this formula is used. So sound pressure level is equal to sound power level plus 10 to the log of q by 4 pi r square. Now imagine sound is from the sound source, it goes basically in a sphere, right? So the area of a sphere is 4 pi r square. So that's how you get the 4 pi r square. And q for non-directional forces 1. Okay, so for non-directional sources 1. Okay, so this is the formula. We'll solve a sum from this in towards the end. Okay, so these are the sound pressure level formulas. Then you have something called as the inverse square law. Inverse square law basically is I is inversely proportional to the distance from the sound square to the square of distance from the sound source. But what it means in basic term is whenever the distance between the source and receiver doubles, the sound level decreases by 6 decibel. Okay, so this is what the inverse square law mean. Now I'll give an example. Say this is your source and this is at 4 meter, and this is okay, this distance is 4 meter, this distance is 8 meters. So basically your distance doubles, right? And they're telling you the sound level from the point source at 4 meter is, let us say, 60 decibel. And they're asking you to find what is the sound level at 8 meters. So the distance basically doubles. So that means your sound level decreases by 6 decibel. So 60 minus 6 is equal to 54 decibel. Okay, now imagine they have given you at 4 meters and they're asking you to find at 2 meters. Here the distance halves, so you have to add 6 decibel to it. So at 2 meters it will be 60 plus 6, so 66 decibel. Okay, so I hope this is clear. This is your inverse square law. So we talked about sound intensity, we talked about intensity level, sound level, and we also talked about the inverse square law. Now we'll move on to the reverberation time. Reverberation time, also denoted as RT, and it's measured in seconds. So measured in seconds. So reverberation time is the time taken. Reverberation time is the time taken for a sound to decay by 60 decibel. Okay, this 60 decibel is important. Now, what does this mean? Let us say you have a sound at 80 decibel and the time taken for it to fall by 60 decibel. So 80 minus 60 is equal to 20 decibel, right? So this is your minus 60 decibel. And whatever time that it took is your RT. Okay, so reverberation time is the time taken for a sound to decay by 60 decibel, and sometimes they also call it as RT60 just because of that 60 decibel. Now I'm gonna draw a graph to show you that. Let us say this is time and this is your sound level, and you have a sound, steady sound, and the sound stops here and the sound decays. Okay, and this is your background noise. So let us say this is, again we'll consider same value 80 decibel, and this here is your 60 decibel. So whatever time it took, right? So whatever time it took is your RT. Now sometimes when the sound is decaying you have spikes in the graph. So again I'll draw this. Again a steady, okay wait, this is dB again, and this is time again. So you have a steady source, the sound stops, the sound is decaying, and sometimes you have like these spikes. Okay, so these spikes, whatever spikes that you see is your fluttering echo, not is your flutter echo. Okay, so flutter echo, and the main reason for you to have flutter echo is because of parallel walls with reflective surface, and I'll talk about the reflective surface in a bit. Okay, with reflective surface. Okay, so RT is clear. Now let me just give basic RT for different spaces. So you have spaces, RT, and the logic to remember it by. So imagine, okay, first you have recording rooms, recording studios, recording rooms, or control rooms. There you need a lot of clarity. Even tiny bit of echo could destroy the recording and the control room. So you'll have very small RT. You'll have 0.3 to 0.5. Okay, then you have classrooms or lecture halls. There your speech should travel like long distance and everything. So you have slightly okayish RT. So 0.5 to zero point 0.8. Then you have auditoriums and theaters. Here you'll need a speech plus music. Always remember that when open music is involved. I'm not talking about recording studio. Open music is involved. You need to have a lot of RT to create this reverberation effect, so that there is richness in music. So you'll have auditorium plus theater, and here the RT would range from 1.5 to, sorry, it range from zero point 0.8 to 1.2. And then you have concert hall, or opera house where a lot of music is involved. So you'll have longer RT to create richness in music. So you'll have 1.5 to 2. Okay, so whenever there is more quiet space is required, you'll have zero point 0.3 to zero point 0.5. In classrooms, your speech needs to travel long distances, so you'll have zero point 0.5 to zero point 0.8. In auditorium theater, it's a mixture of both speech and music, so you'll have zero point 0.5 to 1.2. Opera house and concert hall needs to have like a longer tick to create this reverberation effect, so you'll have 1.5 to 2. And lastly, let's also see offices or homes where you just need to have normal conversation level, RT. So that is zero point 0.4 to zero point 0.6. This is normal conversation. Okay, so this is RT for different spaces. And let's move on with the formula for finding RT now. RT is equal to 0.16 into V by A. This is known as Sabine's formula, where RT is reverberation time, V is volume of the space or room, A is total absorption. And remember, this formula is used only for metric values. Like your volume should be in cubic meters, and total absorption. I'll talk about total absorption later. But remember, your all your surfaces and everything should be in meters. So this formula is for metric values. You have an imperial for formula as well. It's just similar. You'll just put a different constant. So for imperial values, your RT would be 0.049 into V by A. So everything is same. You just change the RT. Mostly in questions you'll have only metric values. So just remember this formula. But this is for imperial values. Now, what is total absorption? Total absorption, okay, before that, reverberation time is measured in seconds. Okay, now, total absorption A is the summation of the surface area. I'll just write it as A1, sorry, A surface area multiplied by the absorption coefficient of the surface. Okay, so what is absorption coefficient now? Absorption coefficient is denoted as alpha. So absorption coefficient is the ratio of sound absorbed to the intensity of it. Okay. So this is the ratio of sound absorbed to the intensity of it. Now I'll again explain this. Imagine you have a wall and you have sound waves hitting on it. So what does this wall do? It absorbs a part of it and reflects some out, right? So whatever it's absorbed, it's its absorption coefficient. So the ratio between the sound that is absorbed to the intensity on, like the way it's incidented on it, is the sound absorption. Now imagine a scenario where this is your window, and let's say it's open. So whatever the sound is gonna incident is gonna pass through it, right? So it means the absorption coefficient for open windows or doors is 1. And the value for absorption coefficient basically ranges from 0 to 1, and 1 is for like open windows and doors basically. Okay, and there are also different types of absorbing surfaces. So you have acoustically reflective surfaces, right? Like whatever waves is incidented, everything is reflected back. So all waves reflected. Then you have acoustically absorbing, acoustically absorbing surfaces where some of the waves that is incident on it is absorbed and only part of it is reflected. Okay, so some of the waves are absorbed. And you also have acoustically diffusing surfaces, which means the waves that hit is sent back in diffusing waves, like it's like scattered or diffused this way. Okay, so there are basically three types of acoustical surfaces, and we talked about absorption coefficient, and I'll talk about different materials and various absorption coefficient for it in a minute. But before that, let's go back to the reverberation formula, Sabine formula. So here your total absorption is the surface area in multiplied by the absorption coefficient. So its unit is sometimes it's written as meter square Sabine, or you can simply write it as Sabine. And it's not necessary that all your surfaces will have the same absorption coefficient, right? Your walls can have something different, your floor can have a different coefficient, your ceiling can have a different coefficient, maybe you have a window open. So all those play a factor in finding your total absorption. So your total absorption can be written as A1 into coefficient of that multiplied by plus A2 into alpha 2 plus so on till A1 into alpha n. Okay, so this is your reverberation formula, which is Sabine's formula. And sometimes, like, they use this formula, but it's mostly not asked in gate, and do not use this unless and until it's specified. There is also a formula called as Erying formula. Okay, and this is used whenever your absorption coefficient is more than 0.2, and they use this formula because it gives a more accurate RT than when you use it in your Sabine's formula. But do not use this formula until it is specified in the question for you to use it. Okay, so RT is equal to 0.16 into volume divided by minus total surface area into ln of 1 minus absorption coefficient. Okay, so this is the formula for it, but do not use it unless it's specified, because this could give you a different RT and you might lose marks. So that's why I'm telling you total surface area. Alpha is the absorption coefficient. V you know, RT you know, L is natural logarithm. Ln is natural logarithm. You'll have like ln written in your scientific calculator, and whenever you are practicing question, try to use the scientific calculator so that you get used to it, because you need to be sure when you are putting the brackets and everything correct so that you get the correct answer. So it's kind of a tricky thing. Okay, so concentrate on that, practice on that. Now let's talk about the absorption coefficient for different surfaces. And this is at 500 hertz. Okay, whatever value I'm gonna give is for at 500 hertz. Now for highly reflective surfaces, so mostly hard surfaces like marble, concrete, glass, brick, they all have really less absorption because a lot of it is reflected, right? So 0.01 to 0.05. Then you have moderately absorptive surfaces like wood panels, heavy curtains, human body. Human body is also, yes, it's also sort of, you also observe sound. So human bodies and furnitures in your room, they all are moderately absorptive, so they absorb around 0.2 to 0.4. Then you have good absorption or good absorptive surfaces like soft surfaces here. Okay, so you have like carpet, fabric wall, acoustical tiles, even foam. These all are softer materials and they have good absorption of zero point 0.5 to zero point 0.8. Then you have highly absorptive material. So excellent absorptive. So excellent absorptive material are mostly porous in general. Okay, so they range from rock wool, glass wool, foam. Again, some different categories of foam. So zero point 0.8 to 1. Okay, so these are the different categories and its absorption coefficient. So the best easy way to remember them is, if you have a hard surface, it has very less absorbing properties in it, so it's mostly reflected back, so it'll range from zero point 0.1 to zero point 0.5. If it is semi hard and semi soft, like your wood, furniture, all those things, then they'll have like zero point 0.2 to zero point 0.4. Your soft materials like your carpet, like fabric walls, all those, they have a good acoustical absorption coefficient, so they range from zero point 0.5 to zero point 0.8. And highly absorptive materials are porous in nature, so you'll have rock wool, glass wool, and they range from zero point 0.8 to zero point 0.1. And I also talked about the RT for different places. Okay, and now let's move ahead. So they could ask you these questions. Let us say this is your auditorium, and we are going to consider two scenarios. These are your walls, and they can ask you what shape of roof is best suited for auditorium, and they'll give you options like, flat roof or pitched roof, concave roof, convex roof, and we'll see which is the best. So the answer is convex curve roof. Okay, so what is a convex roof? Okay, so it's like it curves outward, so that is your convex roof. And imagine you're standing here, so whatever that sound or whatever you're speaking or you're performing, it reflects and comes back uniformly. So here your sound distribution is uniform. Okay, this is the right answer. But let's also consider a concave curve. Imagine you're standing here and you're speaking. Whatever you speak is concentrated towards one spot because it's a concave curve. Okay, and this leads to something called as sound focusing, which is basically it creates a hotspot. And that is why concave roof is not advisable. And here you do not get an uniform fusion of sound is not achieved. Okay, so these are the roof structure for acoustical purpose, and we are done with the theory part of acoustical, and we'll look into sums in the next video.